Let's review some acid-base concepts. So there are a few different definitions of acids and bases. We'll mostly be focused on Bronsted acids and bases, but some Lewis acids, which we've already talked about in our course so far. Now remember that a Bronsted acid is a molecule that donates a proton. A proton is a hydrogen without any electrons. So we can draw that as H+. We refer to it as a proton because a hydrogen atom, a neutral hydrogen atom, has one proton and one electron. If a hydrogen does not have any electrons, then all it is a proton. So a Bronsted acid donates a proton and then it accepts electrons. So typically we see this where the acid molecule has a bond to an acidic hydrogen. The hydrogen will be removed by the base, so it's donating the proton, and then the electrons in the bond between the acid molecule and the proton that's removed will then be owned by the acid molecule. So that's a Bronsted acid, and then a Bronsted base accepts the proton. So anytime we see a proton transfer in a mechanism, the molecule that starts with the proton but loses it is the acid. The molecule that ends with the proton is the base. We describe the acidity of molecules with acidic protons, so the acidity of Bronsted acids with pKa values, where more acidic molecules have lower pKa values. So the lower the pKa, the more acidic that proton is on the molecule. We have a pKa table that we'll be using in class, and that tells a bunch of different pKa values so you can see specific pKa values for specific molecules. But as we've talked about in Organic Chemistry 1, different factors, different properties of molecules can impact the acidity of that molecule. So let's compare three here: water, ethanol, and ethane thiol. Thiol might be an unfamiliar suffix here. Anytime you see this, this means we have a sulfur present. Okay, so water, H2O, we know the structure of water. It's pKa, and we'll write out all of the pKa's. Is about 14. Ethanol, its pKa is 15.9. Now comparing water and ethanol, the change is that we now have a carbon chain, the CH3CH2, where there was a hydrogen. If we start with water and then compare it to ethanol, that's the difference. If we think about our previous unit, our group's alkyl chains, hydrocarbon chains, are electron donating groups. So the electron donating effect of the ethyl group is that it decreases the acidity of the proton that's bonded to oxygen. So because we have an electron donating group, that decreases the acidity of that proton. Let's think about that in opposite terms. If we're thinking about what makes a proton more acidic, if we have something in the molecule, and we'll talk about that in a little bit, that pulls electron density away from the hydrogen, that makes it more acidic. It has a stronger partial positive charge. It's more attractive to a base molecule. So that makes a molecule more acidic. But in this case, we have our electron donating group. So that's adding electron density to the hydrogen. So let's write a little bit out here. This is slightly less acidic than water. Because CH2CH3 is an electron donating group. Now let's compare ethane thiol. So we have the ethyl group. Now instead of an oxygen, we have a sulfur. The pKa of ethane thiol is 10.5. So it's more acidic than both water and ethanol. The more similar molecule is ethanol. The only thing that's changed between ethanol and ethane thiol is that we now have a sulfur instead of an oxygen atom. If we look at the periodic table, sulfur is one row below oxygen. So it is a larger molecule, and that's the best way to explain why ethane thiol is more acidic than ethanol. Because sulfur is larger, the bond between sulfur and hydrogen is longer, so it's a weaker bond, easier for hydrogen to be removed. Also, because sulfur is larger, it's more stable with a negative charge with the extra pair of electrons as the conjugate base. All right, so ethane thiol is more acidic due to atomic size. There are two different trends that we've talked about so far. There are certainly more that explain the difference in pKa values for different molecules. But now let's think about if we have ethanol and a hydroxide ion in solution. So what is present in solution when both ethanol and a hydroxide ion are present? So if we have ethanol, let's draw that out here. Okay, so ethanol has a pKa of 15.9. Now if we have hydroxide ion in solution, that's OH minus. Oftentimes, the way OH minus is actually added to solution is by adding sodium hydroxide. Remember that sodium is a spectator ion, which means it does not participate in the reaction. It's only there really to balance the charge. That's the way that we use it when we're writing out molecules this way, writing out a reaction this way, is that we use that to balance charge. So you might remember that hydroxide, the OH minus ion, sodium hydroxide, that's a strong base. So if we have a strong base in solution with ethanol, which can act as an acid, the base, which is a proton acceptor, creates a new bond to the acidic proton. The acid is donating the proton and accepting electrons that were in the bond to the acidic hydrogen. This is an equilibrium reaction, and our products are the ethoxide ion. Now we can write in sodium to balance out that charge. And then we have water. The water is our conjugate acid. The pKa of water is 14.0. When we look at acid-base reactions, especially Bronsted acid-base reactions, we can describe whether the reaction lies to the right or to the left based on pKa values. Reactions lean towards the side with the weaker acid, so the side with the higher pKa. If we compare our two acids, ethanol and water, ethanol has a higher pKa, so it is a weaker acid. And that tells us that equilibrium lies left or to the reactant side. And we can represent that with the equilibrium arrow between reactants and products, having a longer arrow towards the reactants and a smaller arrow towards the products. One more trend I want to describe in this video is thinking about how polarity affects acidity. Here are two examples where we'll compare ethanol again to another molecule. Let's write the pKa again, 15.9. And then we'll compare to a molecule where instead of having a CH3 group, we have a CF3 group. So CF3, CH2, OH. The pKa of this molecule is 12.4. So a lower pKa, and that's because we have this electronegative atom here. This pulls electron density away from the acidic hydrogen that's bonded to oxygen. That increases the partial positive charge on that proton, making it more acidic. Also helps stabilize the conjugate base with the extra electrons, the negative charge. And this is what we call the inductive effect. So the electronegative atom pulls electrons, which makes the hydrogen more partial positive has a stronger partial positive charge, and then this is the inductive effect. The more electronegative atoms, a greater number of electronegative atoms in a molecule will have a stronger effect. And the closer the electronegative atom is to the acidic hydrogen will have a stronger effect as well.